graph that. We want to say, how does this interaction change there? Jillian?
Wouldn't it depend on the enzyme, the optimal temperature at which it functions?
Yes, yes. But that doesn't affect, it doesn't affect the general shape of the curve, but I'll show you in a minute. It affects where the curve sits here. I'll show you what I mean. But yeah, you're right on that. It depends on where this enzyme is supposed to work. But let's assume this is an enzyme in a human. What do you think the optimal temperature would be for enzyme catalyzed reactions in a human? 37 degrees Celsius. So we would assume then that at temperatures below 37, right, things aren't going to work as well. And temperatures above 37, things aren't going to work as well. So what's the shape of the curve? Which one? A bell curve, right? So it's going to look something like this. Now, will it be exactly that pretty? No. But what it will be is that there will be a peak. And the peak tells us something. What does the peak tell us? The peak tells us the optimal temperature for this reaction. And that's the optimal temperature. So Jillian, this is what I was talking about before. When you ask that, yes, it does matter what specific enzyme we're talking about and what organism. The shape of the curve will be the same. It might just be shifted one way or the other this way. There are organisms that live under very, very high temperatures. So their enzymes are specialized for higher temperatures. So the curve shifts a little bit to the right. There are organisms that live in very cold environments. So their enzymes function best under colder, so the curve shifts to the left. But it looks like this. So it shows an optimal. Now, the reason you get the shape of this curve is really for kind of two different reasons. Why does interaction increase with temperature? What's that? More what? Exactly. Molecules move around faster, right? You know, every molecule, because electrons are moving in it, in the molecules, right? Electrons move. And because electrons move, every molecule has a little bit of what we call vibrational energy. And that's because of these electrons moving around in orbits and shells. Now, that vibrational, right, electron energy, right, is called Brownian motion. And that causes molecules to move around. So what can you do to make molecules move around faster? Is you add energy to it, right? They'll move a little bit on their own because they have their own inert energy. If you add energy by adding heat, things move faster, right? So if you heat things up, right, I mean, just think about it. What, you know, does your sugar dissolve faster in a hot cup of coffee or a cold cup of coffee? A hot cup of coffee, right? Because we're speeding up that process. So here, what we're adding here, the reason this is increasing is because we're increasing energy. I'll just abbreviate that K sub E. Right? So we're adding energy by adding heat. But there is a kind of a point of no return here, right? That if you keep adding heat, obviously we're still adding energy, but something is happening to cause the reaction or this interaction to decrease. And what's happening is that as you add heat to this protein, it causes it to fall apart. And it's called, at the strictest sense, it would be called denaturing. So even just under mild temperatures here, it's changing its shape here. So it's not working as well. But down here, it doesn't work at all. And down here, it's completely denatured. And denaturing of a protein is simply this. It is reducing it from its three-dimensional shape to primary structure. So you're causing it to go from this folding right here, which we know it has to have to be a protein, right, to be able to bind, to just a polypeptide, just a chain of amino acids. And it won't do a thing. Okay. So this here, what we're doing here, the reason we're decreasing down here is because of denaturation. Does that kind of make sense there, the physical environment? So So you get a fever, which, by the way, is a body's natural response to an infection, not the infection doesn't cause the fever, the body causes the fever in response to the infection. We'll talk about that, why, a little bit later, but when you have a fever, you slightly raise your core body temperature. And guess what? You feel what? You feel a little sluggish. Things don't work as fast as they should or as good as they should. Why? Because you are changing your body's own ability for these proteins to interact. You don't really start getting full-on denaturation until about 45 degrees to 50 degrees Celsius. And let me tell you this, if your body temperature ever got to 45 degrees Celsius, we might as well serve you for dinner because you're cooked. Honestly, if your body temperature gets up to 40 degrees Celsius, you probably would start convulsing. It's just out of the, it's just too hot. Things don't work as well. Neurons don't work as well under high temperature. That's part of the problem. So your brain starts doing funny things.
When do you start hallucinating?
But you want